So in this session, we'll have a little more look at the memory management unit of 80286, 386 and 486. So we were talking about memory management unit with respect to virtual memory. So as I said, the memory management unit is going to handle virtual memory. So the memory management unit is functionally positioned between the processor and the actual memory. So whatever address is being generated internally by the processor would be, this is functionally because your memory management unit is also going to be present within the processor only. So there is going to be the memory management unit which is within the processor. Then you are having your actual external memory available, and whatever is going to be the address will be taken by the memory management unit. It is going to be translated and it is going to be given to memory. So we say functionally the memory management unit is going to be between the processor and the actual memory. Now when you are writing the ALP, you would write them with logical addresses. You would have written them with labels. The program is going to be assembled. Whatever is going to be the logical address is replaced by segment and offset in case of 8086. In case of any system, 80286 or 386, there is going to be a segment and offset. So in case of 286 or 386, this segment is going to be treated as a selector because from 80286 onwards, we have a memory management unit. So this memory management unit takes the segment value, treats it as a selector, and from the selector it is going to get a descriptor. So the descriptor, basically we know what it does. It gives the base address of the segment, it gives the privilege level of the segment, and other than that it has a few control bits which determine the type of segment, what is going to be the size of the segment, etc. So essentially what is going to be done is the memory management unit takes the logical address, it converts it into the physical address. So that is what is going to be carried out by the memory management unit. The selector bit is going to point towards the segment base address. The segment base address will be added with the offset in order to generate the physical address. This is going to be in case of 80286. The presence of the memory management unit allows 80286 to have up to 1 GB. We talked about the virtual memory in 386 and 486 in the previous session. It can have up to 64 TB of virtual memory based on the concept of segments and pages. So segments will have selectors, pages will have descriptors, and so on. Now, what exactly does the memory management unit do? When it gets a logical address, the memory management unit first checks to see if the segment is going to be present in memory or not. So the moment the logical address is going to be generated, it checks and sees whether the segment is present in memory. If the segment is going to be present in memory, it will know whether the segment is present or memory from the descriptor. We know the format of the descriptor of 80286, 386 and 486. There is one bit which is going to say whether the segment is available in physical memory. If a segment is available in physical memory, it will calculate the physical address based on the descriptor and the offset. If the segment is not present, an interrupt is going to be raised. Now, as part of the interrupt service routine, you should write that interrupt service routine. It is not automatically written by the processor. It is available in the operating system, or you can write that interrupt service routine. This interrupt service routine will read the code from the hard disk drive and transfer the segment into memory. This operation is essentially semi-automatic. Your operating system automatically takes care of it, and hence whatever might be the delay is negligible. A well-designed, well-structured memory management unit will give a hit of 90 to 95%. So when you say it's a hit rate of 90 to 95%, it means whatever is a segment that is accessed, 90 to 95% of these segments will already be available in memory. If they are not available in memory, they have to be then loaded from the disk into the memory, and that is done by the interrupt service routine. That is not done by the memory management unit. What the memory management unit is, it checks whether the segment is available in memory. If available in memory, it generates a physical address. If not, it just raises an interrupt. And it is the operating system's ISR that is going to load the value from the hard disk drive into the main memory. Generally, the delay we consider it to be negligible. So other than that, the memory management unit gives one more function. That is going to be the memory protection function is provided by the memory management unit. We know that the selector has a privilege level. The descriptor also has a privilege level. If the segment selector's privilege level happens to be greater than or equal to the descriptor, then we allow access. Remember, we call this our request privilege level and we call this our descriptor privilege level. We discussed this in the earlier modules itself. This is called as RPL, this is called as DPL. If the RPL is greater than or equal to the DPL, then access is going to be allowed. So that's how memory protection is going to be implemented by the hardware. Hardware implements the memory protection by making use of the RPL and making use of the DPL. Now, before we go on and look at the memory management, let's look at some of the special registers which are used for implementing the memory management features such as virtual memory and protected memory. So we have the machine status word. This machine status word is available in case of 80286. In 80386 or 486, it becomes the CR0 register. So what does this machine status word indicate in 80286? The first bit is called as protection enabled. So this indicates whether memory protection has been enabled or not. If it's disabled, privilege levels don't matter anymore. So there is no memory protection. Any task can access any data. It can access the operating system's data as well. So no memory protection is going to be there. The next bit indicates whether a coprocessor is present. In 80286 and 386, these bits are valid because you might have an arithmetic coprocessor. In 80286, the arithmetic coprocessor is going to be 80287. Now there is one more option provided for the coprocessor which is called as emulate coprocessor. Now what happens is, whenever you're executing an instruction which is going to be a floating point instruction cannot be executed by 286. So we have our main processor which is 80286 which has its own instruction set, and we have 80287 which is a coprocessor and it has its own instruction set. The instructions of 80287 would be the floating point instructions. It could be exponential, it could be logarithmic instruction, tangential instruction. So those are available in 80287. In 80286, you have the normal integer data transfer instructions. Now all of this is going to be present in a common memory area. So any floating point instruction of 80287, for instance, one floating point instruction is floating point multiply. So this floating point multiply instruction will be available in the same main memory as an 80286 instruction. So for instance, I might have move AX, BX, and this might be followed by a floating point multiply instruction which might multiply the contents of the AX register with the BX register. This FMUL instruction, of course, cannot be executed by 80286. So such instructions, the assembler automatically puts an escape prefix. An escape prefix would mean that 80286 would treat this instruction as a no operation, and 80287 will be executing the FMUL instruction. So it doesn't mean that there is a separate memory area for 80286, a separate memory area for 80287. Same memory area, your normal instructions will be mixed up with the floating point instructions. The normal instructions are executed by 80286, but a floating point instruction comes with an escape prefix. So this instruction will be treated as no op by 80286 and will be executed by 80287. In case you don't have an 80287 which is present in your system, then in that case, if an instruction has an escape prefix, interrupt 7 will be raised. Now in response to the interrupt 7, what is done is there is an ISR written. This ISR will actually implement the fmul instruction. You can do floating point arithmetic. You can do floating point arithmetic of multiply of two data. For instance, you can multiply data 16.2 with the data 17.1. But the only thing is the ALP which you write for this would be pretty long. Now what you will do is every time there is going to be an escape instruction and there is no coprocessor, the 80287 is not going to be present, and there is an instruction which says escape and fmul is going to be there. So what happens is interrupt 7 is going to be raised. As part of the interrupt service routine, you can write an ALP to actually multiply two floating point numbers. It can be done by writing an ALP. The only thing is it will take a lot of time for execution. The main advantage is you don't need to have 80287, so you're cutting down on the hardware. But since you are implementing each and every floating point instruction by a very long ALP, it will take a long time for execution. So that is called as the emulation mode. There is no 80287, but then every time an escape prefix is detected, ISR will be executed for interrupt 7, which will have an ALP to execute the floating point instructions. So that was emulate the coprocessor mode. The next bit is called as task switching bit. Whenever the processor moves from one task to another, when the switching is going to take place from task 1 to task 2, automatically this bit is going to be set. Every time task switching happens, this bit is going to be set. It is a status bit. It indicates that task is being switched. It doesn't enable task switching. It indicates that task switching has happened. So these are the 4 bits in the mission status word of 80286. Now there is going to be, in case of 80386, 4 special registers which are used for the concept of virtual memory. 80386 implements virtual memory in terms of segmentation and paging. So these registers are going to be the registers which are ZR0 to CR3. We already know about this PG bit which is going to be present. So this PG bit is going to be used for enabling paging. PE, MP, EM and TS are already available in case of the mission status word of 80286, and they have the same meaning here. What is going to be different is going to be the bit which is ET. In case of ET bit being set with 80386, 80287 is used as a coprocessor. Generally with 80386 you are supposed to use 80387 as the coprocessor. But if this bit is going to be set, this is going to make use of 80287 as the coprocessor. Then of course we know what is going to be the purpose of the page directory base. So other than the 12 bits which are going to be present here, there is going to be the page directory base. This points towards the beginning of the paging table. And paging table in turn is going to point towards the beginning of the page. This was how paging was implemented. So the paging directory base is going to point towards the paging table. I am not going to pick up this particular control register because to talk about paging faults is way beyond the scope of this course. When you do a course on advanced computer organization or computer organization, you will be able to understand the concept of paging faults. So you hold the idea of paging fault until you come to a course on computer organization. But what we are interested in is the protection enable and the task switching. So these are going to be the 2 things which are actually handled by the memory management unit, other than of course the paging which is handled by the page directory base. So these are the special registers, and this is how virtual memory is going to be implemented. Now what is going to be important for us here is the implementation of virtual memory as we saw it earlier. We will look at memory protection with much more detail. what we are interested in is the memory management unit's virtual memory function, where any address received, the memory management unit actually checks if the segment is present in memory. If yes, it calculates the physical address. If the segment is not present in memory, it is going to raise an interrupt to the processor. And as part of the ISR, the operating system reads the code from the hard disk drive and transfers it into memory. So that is going to be the function of the memory management unit, to detect whether a segment is present. If the segment is not present, raise an interrupt. If the segment is present, it converts the logical address to the physical address. So this is going to be the virtual memory part of the MMU. How this conversion is done, we have seen this already. So what we will see next is going to be the memory protection and how memory protection is going to be implemented in 286, 386 and the 486 processors. So I'll stop with this in this session.